The first category of vibration we're going to look at is this free undamped vibration. So remember, with free undamped vibration, that means the forcing function equals 0, which is why we have a 0 here on the right side of the equation. And the undamped part means that the damping coefficient b equals 0, which is why there's no by prime term here, because that damping is 0. So it essentially simplifies our equation and leaves us with just my double prime plus ky equals 0. Now let's think about what happens to the solution of this. Let's think about the solution in general, and then we'll do an example with specific values for m and k. As you solve this, you would set up first the characteristic equation, because we're solving a homogeneous second order equation. So this would look like mr squared plus k equals 0. And solving for r is pretty simple. You just subtract k on both sides and then divide by m. And then take the square root. So r would be plus or minus the square root of negative km, or k over m rather. Now since k and m are both positive values, this leads to a complex solution. So we would say r equals 0 plus or minus the square root of k over m times I. And to make things simpler, we're going to call that square root of k over m, rather than carrying that around in all of the formulas, we're going to call that omega. And this omega, as you'll see in a minute, is going to be related to the frequency. It's called the angular frequency of this vibration. And so it'll control how fast this thing oscillates. Which basically means for larger stiffness values or smaller masses, this would vibrate much more quickly. But larger masses basically have more inertia, and so they would vibrate more slowly. And lower values for stiffness would also vibrate more slowly because it wouldn't basically wouldn't catch up fast enough to the vibrations. So you can kind of think about how those values of k and m would control the frequency of vibration, which is why we call this omega for frequency. So going back to the familiar forms for these homogeneous equations, with this complex form, our alpha is 0, and our beta is this omega. So the solution looks like this, where we have y of t equals c1 sine of omega t plus c2 cosine of omega t. And again, that omega is the angular frequency, so it relates to how quickly this oscillation happens. So that's one way to write down the solution. There's another way to write down the solution, which may be more convenient sometimes, and we'll show an example perhaps where it would be more convenient. I'll leave some of the details of this algebra to you, or you can look them up in the textbook, but it turns out that you can also write it this way. And if you remember your pre-calc class, this may look, or should look familiar, hopefully. We can essentially convert this combination of sine and cosine into a single sine function that will show us more clearly what the frequency, what the amplitude, and so on is of this, this curve, phase shift, and other things like that. All those terms that you learned about back in pre-calc. And the connection between these two is that a is going to be the square root of c1 squared plus c2 squared. And the tangent of this phi, this angle here that relates to the phase shift, that equals c1 over c2. Again, I'll leave the details out here just to avoid too much complication, but the details are in the textbook. You can look those up. We're more interested in kind of using this. That's really a pre-calc problem to convert one into the other, so I'll leave that alone. But you can also write the solution this way. So whichever is more convenient, we'll take advantage of as needed. But the idea here is that the essential shape of this is a sine wave with some amplitude, some frequency, and some phase shift. So roughly speaking, the position looks more or less like this, where we've got a wave that does this. Now notice, by the way, that if you're thinking about these sine waves in general, there's one piece that isn't included in this formula that could be included. If you remember back in pre-calc, there was also an option to have a vertical shift here at the end. And notice this one doesn't have any vertical shift. In other words, the oscillation happens around the t-axis, or around y equals 0. And so what this looks like is, as this object vibrates, it's here, and then it starts vibrating around this center line. So we do something like this, where we go up and down, but always right around the center line. And notice that this oscillation doesn't slow down. Since there's no damping, there's nothing stopping this from continuing on forever, and there's no forcing function. So if we included gravity, gravity would eventually slow it down, but without any damping, in theory, this thing continues on forever without slowing down at all. So this is kind of the most basic option for an oscillating mask like this, is if there's no damping and there's no forcing function, it simply reduces to a bare sine wave and just bounces back and forth and cycles forever. So if there's no damping, that's what that does to it. So this thing just cycles on and on and on without end. So that's what free undamped vibration looks like in general. Now we'll do an example in the next video with some numbers on this, but you'll see the results just end up looking like this.